Alright, welcome back. This video is about something called a linear first order differential equation. And these types of equations have this format, have this anatomy, that the derivative of the mystery function plus some known function p of x times the mystery function y is equal to some other known function q of x. So y is the only part here that's unknown. The p of x and the q of x are part of the expression. They're given to you. Some examples of first order linear differential equations are shown here. We have dy by dx plus 1 over x times y is equal to negative x squared. Here's another one. dy by dx plus 1 over x ln x times y is equal to 1 over x. Is there a third one? No, there's not. Now this p of x and q of x that are written up above, those labels are actually important. They're going to be necessary to work with when we talk about solutions. So I'm going to identify what p of x and q of x in each of these examples would be. So in the first example, p of x, the part that's multiplied by y, is equal to 1 over x. And q of x, the function of x that's all by itself, is equal to negative x squared. For the second example, p of x is equal to 1 over x ln x, and q of x is equal to 1 over x. I'm going to spoil the ending for you. I'm going to spoil like the big reveal for the formula for how to solve a linear first order differential equation that has this dy by dx plus p of x times y is equal to q of x format. We're going to have to create this object called an integrating factor. It's called I of x, and it's equal to e to the power of the antiderivative of p of x. So whatever the p of x is inside our differential equation, we're just going to integrate that, get a new function, and put e to that power, and call it I of x. Once we have that, we plug it into our big formula, our big solution formula that tells us what the mystery function is. So our mystery function is going to be 1 over I of x, 1 over this integrating factor, times the integral of q of x times our integrating factor. One of the benefits of this method is that it gives us y all by itself at right from the start. We don't have to rearrange. We don't have to exponentiate or log both sides or square both sides or root both sides or do anything like that. It's already going to be y equals a function of x. The downsides of this method are just the usual downsides of integration. It may be difficult to find the antiderivative of p of x. It may be difficult to find the antiderivative of q of x times I of x. That's where the challenge is going to be. But why? Why does that structure solve that particular type of differential equation? I'm going to answer that question in 2 steps. The first step is a derivative exercise. How do we take the derivative of our integrating factor times y? And we'll see why that expression is important in the second part of the proof. So let's take the derivative of e to the integral of p of x dx times y. I'm going to rewrite that in a little bit of a nicer form. This is the derivative of e to the w times y, where w is a function of x and y is a function of x. So we're going to need a product rule. We're going to have the first function times the derivative of the second. I might as well write down product rule. Plus the second function times the derivative of the first. And the derivative of e to the w is e to the w times w prime. Well, what's w? W is the integral, or e to the integral, integral of p of x dx. We just said w is the power inside the exponential. So what's w prime? W prime is the derivative of the antiderivative of p of x. So we take the antiderivative of the function, and then we take the derivative of that. That's just going to give us our function back. So I'm going to plug that in. We get e to the integral of p of x dx times y prime plus y e to the integral of p of x times p of x. Okay, now why does that matter? Why is that derivative special? So I'm going to write down a differential equation. dy by dx plus p of x times y is equal to q of x. And then I'm going to multiply both sides by 1. I'm going to use a fancy form of 1. So 1 times the left-hand side is equal to 1 times the right-hand side. I did mention that multiplication by 1 is an extremely powerful way to solve math problems, and here's another example of that. What form of 1 are we going to use? Well, I'm going to use e to the integral p of x, just because. It's an inspired choice. Oh, let's see. I'm only going to multiply left-hand side by 1. I'm going to use e to the integral p of x divided by e to the integral p of x. My apologies. I got overly excited and misspoke. Now I'm going to cross multiply and multiply both sides by e to the integral p of x. And I'm going to distribute the top one into the brackets on the left. So e to the integral of p of x dx times y prime, or dy by dx, I guess. I'll call it y prime, same thing, just less fraction-y, plus e to the integral of p of x dx times p of x times y is equal to e to the integral of p of x dx times q of x. Now what is that statement on the left-hand side? That statement on the left-hand side is the derivative of e to the integral of p of x times y. Compare it. Compare the final answer we got in step 1 up above in blue with what we have on the left-hand side in purple. I guess purple and blue, but mostly purple. So this is d by dx of e to the integral of p of x dx times y is equal to e to the integral of p of x dx times q of x. I'm going to integrate both sides. I'm taking the derivative, and then I'm taking the antiderivative afterwards. Oh, and I should integrate with respect to x. My apologies. Forgot. But whenever we add an integral sign, we have to make sure there's a differential there as well. Okay, so I'm taking the derivative with respect to x, and then I'm going to take the antiderivative with respect to x. I'm just going to get the original function back. So e to the integral of p of x dx times y is equal to the integral of e to the integral of p of x dx times q of x dx. And then I'm going to divide both sides by e to the integral of p of x dx, or I'll just call it I of x. So I of x is, or I of x times y is equal to the integral of I of x times q of x dx. So that means y is equal to, divide both sides by I of x, 1 over I of x times the integral of I of x times q of x dx. The proof is largely mechanical. The one magical step is that step there. Multiplication by 1 and choosing that particular form of 1. That's the magic. You don't have to worry about reproducing this. This isn't for solving the problem. This is so that you know that there's a reason why this formula is the formula for solving the differential equation. And for seeing, what type of process gives birth to a formula like that. And it's a very inspired process. It's not mechanical at all. So it gives you this formula you can use without having to think. But in order to create it, man, you gotta think. You gotta think a lot. And we'll look at examples of using it in the next few videos.